this remarks the last lecture by Professor Arnab, and over to you.
Okay, so thank you. So I'll continue from where I left off in the morning and try to introduce this Fluke MBL, which is a time crystal and therefore needs more structure, as I would hopefully explain to you during this last lecture of mine. But before that, let me just briefly again recap this discussion about symmetry breaking, because apparently there was some confusion. So let me just do that. So let's keep a problem in mind, a very specific problem in mind. So let's say you have this kind of a Hamiltonian, right? And you're just studying the ground state properties of this Hamiltonian, let's say, right? You see, this Hamiltonian has a particular Z2 symmetry. If you just stare at it, the symmetry is the following. This unitary transformation keeps this Hamiltonian invariant. So I go to each side, change sigma z to minus sigma z, sigma y to minus sigma y, and sigma x to sigma x. This keeps this Hamiltonian invariant. So that's a Z2 symmetry of this theory. Okay, and of course, if you write the density matrix of this theory, then that also has this symmetry. So the question is then how can symmetries be spontaneously broken? Because as you might have seen for the transverse field Ising model, if you draw the phase diagram, the ground state phase diagram, then the critical point happens to be at 1 and above 1. So this is just a cartoon of the ground state phase diagram. There's a unique ground state, right? Of course, there are quantum fluctuations here. This is just a cartoon. And below, the ground state sort of either looks like that or looks like that, right? So if you wish, on this side, the ground state spontaneously breaks a Z2 symmetry, okay, on this side, okay? So now, if you look at a finite size system, and let's say you somehow solve for the spectrum of the system, and you see the spectrum here versus here. So you choose some coupling G1 here, and you choose some other coupling G2 here. G1 is sufficiently to the left of this critical point. G2 is sufficiently to the right of this critical point. If you do that, then, so I'm again drawing a slightly inflated version of the low energy phase diagram. It looks like that here, the low energy, whereas it looks like that here. So of course the energy is ordered like this. These are increasing energies. So I hope you can immediately see a difference between the two diagrams, right? Here there is a unique ground state, and this is in a finite system, right? Here there is a unique ground state. Here there are two states which are almost degenerate to each other. In fact, if you look at the gap between these two states, it's exponential of minus alpha times L. Okay? And then there is an order 1 number here. Whereas here, there is always an order 1 number. Okay? So I hope you see the difference between these two pictures, right? So if you go to a really big system size, the difference is here of a 2 versus a 1. Now, all of you know that 2 cannot be smoothly defined to deformed to 1. Therefore, there must be at least one phase transition in between. That's why there is a phase transition. Okay? Good. Okay, so, and this alpha is basically, oh, what was that comment?
What was 2 and what was 1?
Oh, okay. So see, here, if you see, here there is a gap of order 1 and rest of the states. Here there is again a gap of order 1 and rest of the states. But if you look below that gap, there are 2 extremely close by states. So the number is 2 here and the number is 1 here. And in fact, that is why there is a phase transition in between. Okay. Okay. And this alpha is of course a function of G minus GC. In fact, as you approach the critical point, then this alpha vanishes in some particular universal way. Okay. Good. Now, an important thing is, if you look at any of these 2 states, which are exact eigenstates of these theory, do not break the Z2 symmetry. Okay, as we already remarked, these 2 states do not. So, a caricature of these 2 states is this, and maybe just to save some time, I'll just put the minus state here also and that. Okay? These 2 states do not break any symmetry, but these 2 states are also, as I said, they have this funny property. They are long-range correlated cat states, okay, because they are superpositions of macroscopically distinct quantum states. Why are these quantum states macroscopically distinct? Because I can look at a macroscopic property, like some magnetization, and that happens to be one thing here and that happens to be another thing here. So these states are, you are superposing macroscopically distinct quantum states, okay? And a more mathematical way of saying that these are long-ranged correlated states. So these 2 states, I'm talking about these two states. A better way of saying that these are long-range correlated states is that there are definitely certain local operators. There are definitely certain local operators here, which if you measure them in those states, this connected correlation function does not go to 0 even if R goes to infinity. Okay? That's why they are called long-range correlated states. However, on the other hand, physical states do not have this property. For physical states, these guys always decay to 0 as the distance increases. Okay? So a physical state is something like this or that, or any other state which may be a superposition of several states but still satisfies this property. Okay? So this is the defining property. However, the point is, if you start from this state, okay, if you start from this state, then even though this state is not an eigenstate of this theory, and therefore it has some non-trivial time evolution, this state would take exponentially long to tunnel to this state. So if you're looking at the system on a time scale which is reasonably small compared to this tunneling time, you would actually see a symmetry breaking. And that is how symmetry breaking happens around us. Okay? So there's also a classical analog of that. I won't discuss it now, but anyway. And you can even see all these kinds of things in Monte Carlo simulations and stuff like that, right? Okay, good.
You said like if I start from either one of the state, it will go to the other state in exponentially long time. That's what I just wanted to understand.
Yes, that's what I said, yes. Okay, now what I'll convince you, what I'll show you is in this time crystal, a fluke analog of this happens. So see, here these macroscopic states are basically degenerate in energy. Macroscopic cat states are basically degenerate in energy. For a fluke problem, the eigen values lie on a circle. So basically what I'll convince you very soon, hopefully, is that in the fluke time crystal, at least in the simplest version of the fluke time crystal, there are many varieties, something like this happens. Again, there are macroscopic cat states. So macroscopic cat states in the simplest caricature need at least two states to superpose, right? And let's say I denote them by these plus and minus or whatever. So I'll soon show you that in the fluke problem, something like this happens. So of course, there's a huge number of eigenstates on the fluke circle. I'm just showing you some of them. So the unitary matrix for a time crystal, as I already said in the end of the last lecture, the unitary matrix, the fluke matrix for the time crystal, if you diagonalize that, all the states are actually macroscopic cat states, long range entangled macroscopic cat states. So basically, there is a state like this, exactly like that. Of course, not exactly like that, but it has long range correlations, and there is a partner of that. There's some other state like that, and there is a partner of that, and so on. So you see the structure. So there's a very interesting and a non-trivial structure like this here. And the difference is these two guys are degenerate in energy. These two partners, if you wish, are degenerate in energy. But this guy and this guy are pi different in energy, pi different, right, in fluke energy, right, because this is diagrammatically opposite to this. So they are not degenerate in quasi-energy. They are pi distinct in quasi-energy. Similarly this. And this kind of a non-trivial structure would give rise to what is called a time crystal. And here only these two guys have this structure. Here all the eigenstates would have this structure because we are concerned about dynamics. So I'll show you that.
So basically, when you are dealing with Foucault systems, you said that every energy is, like epsilon n goes to epsilon n plus twice pi by t, something like that.
Yes. So but on a circle, there is no ambiguity. That's why I'm drawing it on a circle.
So the point is that if I denote this, if I put these things on a circle, then I should be, so there should be a pair, each one representing a cat state.
Exactly. So there's like a rod. One end of the rod is one cat state, the other end of the rod is another cat state. And see, in any symmetry breaking, there is a rigidity concept. Here the rigidity is the rigidity of the rod. So this thing can shift a bit, but then this thing will also shift. That's the rigidity. But anyway, so at least if you understand nothing from this lecture, just keep this picture in mind. And when you understand it finally, then this picture will make sense. So, okay. So let's try to see that.
And so there are like even number of roots?
Well, of course, yeah, that's a fair point. So, yeah, let's deal with a situation where there are an even number of eigenvalues such that I can pair them. Yeah, if something is unpaired, I would just say that it's measure 0. But yeah. Okay, so there are two very nice papers which really started this subject of fluke time crystals. And in fact, I'll closely follow the logic of the first paper while explaining everything. This is the second paper, which also discussed similar things. Oh, I'm sorry. So I actually interchanged the references. Sorry. This one is 117 090402. And this one is the other one, 11625. Okay, so these two are very nice papers, and I'm following the logic of this paper mainly. Okay, so now there are two equivalent definitions of what is a Fluke time crystal. One is very easy to appreciate in the sense of what is happening dynamically, okay, because after all, we are concerned about non-equilibrium dynamics here. And the second definition is more akin to this. This seems to be a more abstract definition, but this actually makes much more sense if you want to understand what is really going on at the heart of the matter, okay? So, definition 1 of what is a Fluke time crystal. So, the Fluke time crystal is a system, is a Fluke-driven system such that the system fails to synchronize with the drive period. You remember that in the first lecture we said that suppose there's an external drive period denoted by capital T, one of the first things that happen is any local operator, if you follow its time evolution, after a certain small relaxation time, that local operator just synchronizes with the frequency of the external drive, okay? So that's the first thing that happens, but here that thing fails, okay? Here, instead what happens is, if one starts with a short-ranged initial condition. So of course, I've already defined this thing for you. What is the meaning of short range? So connected correlation functions should decay to 0 as the distance between 2 points goes to infinity. So if one starts with any such short range initial condition and then looks at the following. So this is the time evolving many body wave function. Okay, so that's definition 1. So there exists at least some simple local operator. There may be more than one such simple local operators. There exists at least one simple local operator where you can show that that operator does not synchronize. So you can see what's the meaning of that. So suppose you can see that I have taken the limit of T1 being large. So I have already waited a sufficiently long amount of time to allow my system to equilibrate and so on. But even after that, if I compute the quantity at some T1, and then I compute the quantity at some T1 plus capital T, if there is synchronization, these two quantities should have agreed, right? That's the meaning of synchronization, but they don't agree, okay? So that means lack of synchronization. This equation shows us lack of synchronization. On the other hand, what actually happens is, for this.
Why are you not using the word thermalization? Is it different or it's the same?
No, synchronization is more basic than thermalization. Thermalization would have meant that these two things go to a particular value. I mean, I'm even thinking about the more basic aspect than thermalization. Yeah.
So you are driving the system with a time periodic field.
Mm-hmm.
The state is not time periodic.
No, the state is anyway a very complicated object. or local operator, exactly. Because even in the fluky idiot setting, the state does some very complicated thing, as Shubhrato has also discussed, right? So state is very complicated. Yeah, but the local observables are not time periodic. However, for the same operator, which had failed to synchronize, the following happens. For some integer n naught which is greater than 1. And the simplest case is n naught equal to 2, which we will study. Okay? I hope you understand what's happening. So it doesn't synchronize at t. But in the simplest case, let's think n naught equal to 2 first. In the simplest case, if you look at capital 2T, then you see that it synchronizes. Okay, so it's like the problem has a time translation symmetry of capital T. There's a time translation symmetry of capital T, but you spontaneously break it to 2T. Okay, instead this happens, right? You spontaneously break it to 2T. Okay, good. That's the simplest case where n naught is equal to 2.
But the state itself is not returning at n0.
No. The state is a very complicated object. You never follow the state. Look at the state does not return. Look at the operator. State is super complicated. No human being can even comprehend a many-body quantum state. Okay, so forget about the state. Yeah. Okay. Okay, so definition, so this is the first definition. I hope you understand the dynamical aspect of this. Good? Very good. So we'll just particularly focus on this. Definition 2, which is equivalent to this, but at first sight you won't realize it. And definition 2 is something which I've already indicated to you at the top, is what I'll chalk out. Sounds a bit abstract, but basically the point is all eigenstates of the Fluke unitary are necessarily macroscopic cat states. Okay, so they are entangled superpositions of macroscopically distinct states. Okay, and they have long range correlations. Okay. Good. So I already gave you one indicator of how to distinguish macroscopic cat states from physical states. That indicator was this 2-point connected correlation function. There is another nice indicator. Let me just give you that as well. So this is this thing of mutual information. This is this thing of mutual information. So let me define it carefully. Suppose again we are concentrating on some 1D chain. Let me indicate two regions. They can be sort of arbitrary. They are local regions, A and B. So the mutual information is defined like this. So, and there may be some complicated wave function. So you first integrate out everything else but the degrees of freedom in A and calculate the corresponding entanglement entropy, that's S of A. Then you integrate out everything else except the degrees of freedom in B and you calculate S of B. And in the last step, you integrate out everything except the degrees of freedom of A and B. So that's A union B. Okay. This quantity is 0 or positive. and it only vanishes if A and B are uncorrelated. Okay, sorry, unentangled. If A and B are unentangled. Okay, so it vanishes if and only if A and B are unentangled. Okay. So if you compute this kind of a quantity for two patches A and B and make the separation go to infinity, what do you expect for a physical state? What is your gut feeling? It should go to 0, right? However, for those kinds of states or for these kinds of states, it will go to a finite number. Okay? In fact, for the states I drew above, you should be able to verify that it goes to log 2. So please try and verify that, okay, that it goes to log 2. Okay, it would not go to 0. Okay, so that's a crucial distinction between those two classes of states. Here, I mean, this is a very reasonable property. This thing basically says that in these physical states, if A and B are very far from each other, they get unentangled. However, if you take those kinds of peculiar states or the eigenstates of the Fluke unitary in a time crystal problem, and you separate A from B, no matter how far you go, it saturates to a non-zero number. In fact, that non-zero number is log 2 in this particular case. Okay?
Is it right to say that even if the entanglement is 0, the mutual information is non-zero, right?
Even if the entanglement is 0. Which entanglement are you talking about?
A and B are unentangled.
Then it is 0.
No, but I never said anything like that. I did not say that. You said that. No, I never said that. Take those two states. They are very peculiar states. Therefore, they have some peculiar properties. I have given you those two states. Now you can try to compute this thing exactly. If you compute this thing exactly for those two states, you'll actually get log 2. You'll get log.
They know that if A and B are unentangled, then this is 0.
Oh yes, so that means that in those two states, A and B are not unentangled. That's correct. Yeah, they are not unentangled. That's true. They are not unentangled, even if they are extremely far from each other. But that is because macroscopic cat states are very peculiar states, right? So, okay. So now I'll do a trick. The trick is almost like I did when I did this anomalous Anderson insulator. I'll start with a solvable problem, and then from whatever I've told you about many body localization in the morning lecture, I'll show you that even if I make that problem unsolvable, certain properties would remain, and that's how we'll argue for the time crystal.
And the fact that these two definitions are equivalent is...
Oh, let me demonstrate that. Well, I haven't demonstrated that, but let me demonstrate that. Well, roughly demonstrate that, not exactly. So basically, so let's say there are these macroscopic cat states, and another important thing which I have not explicitly stated here is that, you know, these things should come at different quasi-energies, which was sort of explicit in my picture there, right? So suppose there is a macroscopic cat state with quasi-energy W plus. And suppose its partner, where you may have flipped some sign, has a different quasi-energy, this. And let's imagine for a moment this plus and this minus were exactly those states that I drew upstairs, right? So maybe this plus minus are literally those states, just for like some simple demonstration. Now I said that in definition 1, you have to start with an initial state which is a short range entangled state, right? So of course I cannot start with plus and I cannot start with minus. I have to either start with all up or I have to start with all down, right? But that's it. Then the thing cannot synchronize. Because you see, if you had started with this, it would have remained in this because it's an eigenstate of the unitary. But if you start with this, then it goes to that, and there are non-trivial oscillations. And these oscillations never decay. Now the point is that I'll further demonstrate to you that the difference between W plus and W minus is pi in the simplest case. That is why there is a particular symmetry breaking, right? But you can understand that why synchronization is lost already at this level, right? Because this W plus is not the same as W minus. That's it, okay? Okay, good. So now, let's go to a solvable limit. So let me define a particular Fluke unitary, which is this. This guy, which in fact we have sort of seen earlier as well, is what is known in the literature as a pi pulse, this unitary matrix. This is nothing but the rotation about the x-axis by an angle of pi. Okay, this guy. This is the rotation about the x-axis by an angle of pi for all spins. Okay, so what it does is that if you give it a state, so if you hit this operator, so let's call it some x or whatever. If you hit this operator on a state like this, now this is a collective symbol. It means the sigma z component at site 1, sigma z component at site 2, and so on. If you do that, then this will go to this state. Okay, because it's just a unitary rotation about the x-axis by an angle pi. Okay. So it's actually therefore called the pi flux. So that's the first thing. And what is this HMBL? So HMBL is sort of a simple thing at the moment. It's just some disordered problem, but only with the sigma z terms. Some disordered problem, only with the sigma z term. And later on, I would like to put, so let's see, later on, I would like to put this term. But right now, let's ignore it. Okay? So HIX is drawn from minus h to plus h. And let's say, imagine that I want this h to be small compared to the scale of hiz and ji. And let's say right now I in fact put this term to be 0. So let's say for the moment we forget about it, but we'll introduce this back. Okay. Then for this theory, where there is no term such like this, actually it's a trivial time crystal with n naught equal to 2. N naught meaning this n naught equal to 2. Okay. Can everybody actually see that? Or can somebody see that? Suppose I start with any particular configuration of sigma I z spins, right? And I keep on hitting this unitary. And I've switched this term off. Okay, I have switched this term off. I keep on hitting this unitary. Then can you see that the time evolution would automatically be a trivial time crystal with period 2? No, okay, fine. But why would it switch? So let's see. So let me, okay, maybe I go there on that board. So let's retain this thing here. So let's retain this thing there. So let's take, so I want to solve this problem. So okay, and keep applying u of t repeatedly on that state. So let's take a particular state, any state. Let me take this state at n equal to 0. Then I hit it with this unitary. All that would happen is that this pi pulse will reverse all the spins. Then after that, this term will pick up a phase. But it won't change the state, right? Because this is a state which is written in the SZ basis, and this term is diagonal in the SZ basis. So you'll just add a non-trivial phase to it, but it won't change the state, right? So if I'm just looking at the state, at the next instant, this is the state I get. Sorry, not at the next instant. When I hit the unitary first, and then I get this. So this n is really the stroboscopic time, right? Then again I get this when I hit it again. And then I again get this. Similarly, if I take any other state, for example, this state at n equal to 0, then when I hit the Fluke unitary the first time, I get this. When I hit it the second time, I get that, and so on. So now there is a very simple local quantity which shows lack of synchronization, right? Just look at any sigma z operator. For example, let's look at this side. This side is up here. It should have remained up, but it becomes down. But now it becomes up, and then it becomes down, right? And similarly here, right? So you can, for example, look at this. So yeah, so it synchronizes, but with 2 times t. Okay, but this is what I would call a trivial time crystal. But let's look at this problem a bit more carefully, because clearly neither this nor that are the eigenvectors of the Fluke unitary, right? Because when I hit the Fluke unitary on this state or on this state, then of course it changes the state to this or to that. So let me find the eigenvalues and eigenvectors of this Fluke unitary, right? It should be straightforward to find because this is a solvable problem, right? So let's just try to find it. So the thing that is required is to just do some bookkeeping to see what phases are accumulated, right? So I just need to consider sort of the energies here, right? And basically the phase accumulated is minus I times T naught times the proper energy of that state, okay? So you see, in this Hamiltonian, there are 2 kinds of terms. One, which remains the same if you change all the sigma z to minus sigma z, right? What is that term? This first piece. So this is even under sigma z going to minus sigma z. And there is another term which changes sign when sigma z goes to minus sigma z, which is this term. So this term is odd under sigma z going to minus sigma z, okay? So I just want to group the energies like that. So yeah, this is even, and as I said, this is the same for this state. And this guy is odd, so let me put this label there. and this changes sign for this. Okay? Now, if you hit the unitary on any arbitrary state like this, then the resulting thing is the following. You can just compute these energies straightforwardly yourself. So, you see, first the pi pulse would hit. So then whatever the state is would go to minus sigma z. And then you have to calculate this classical phase factor, right? So because of that reason, the computation looks like this. The computation of the phase looks like this. The state is, of course, minus of sigma z. And see, here this term has minus sigma z and this term has plus sigma z simply because of the reason I said. First, this part hits. So that makes sigma z go to minus sigma z. Then you look at this phase accumulated, but the state has already gone to minus sigma z. So I have to use that definition here in E minus because it's sensitive to the sign of this thing, but here I can just use E plus of the original thing, right? So, okay. I'm doing nothing very complicated, so if you just stare at it, you'll immediately see this thing. And similarly, for this state, I have exactly this, but here I have something different. And of course, this state also toggles. So then this is the unitary matrix. This is just a 2 cross 2 matrix, and I can just diagonalize this unitary matrix. So let me just write the eigenvectors and the eigenvalues of this unitary matrix, right? Everybody understands why in this solvable limit, this giant unitary matrix just decomposes into 2 cross 2 blocks, right? Because for this solvable limit, this unitary matrix only connects sigma iz to minus sigma iz and minus sigma iz to sigma iz. It doesn't connect it to any other state. Therefore, this giant unitary matrix splits up into 2 cross 2 blocks. And these are trivial to solve, right? So let's just solve them. So I'll just write some expressions. You can verify later that they are correct. So the eigenvectors of u of t are, if you just concentrate here, this is the coefficient times this state plus minus. So there are 2 eigenvectors because of course it's a 2 cross 2 matrix. I t naught E minus sigma iz and just to normalize it, divided by square root 2. And the corresponding eigenvalues are plus minus e to the minus I t naught. And see, the eigenvalues only depend on E plus. So that's the nice thing. The eigenvalues only depend on E plus. Okay. So notice that the eigenvalue is a complex number, and as it should be, unimodular complex number, and in one case there is a plus sign and in the other case there is a minus sign. So please notice 2 things immediately. The eigenstates are macroscopic cat states. All of you agree, right? Because this thing and this thing are macroscopically distinct states, right? This thing and this thing have a clear macroscopic distinction. Whatever the spins are here, the spins are opposite here, right? So there's a macroscopic distinction. right? So these are macroscopic cat states. So whenever you produce a quantum state where you superpose macroscopically distinct states, that's a macroscopic cat state. Okay, so that's the first thing. The eigenvectors are macroscopic cat states. And look at the eigenvalues. That's also interesting. There's a plus sign here and there's a minus sign here. So if you draw it on the unit circle, if one guy is here, the other guy is necessarily diagrammatically opposite to it. You understand, right? Because the minus sign can be represented as e to the I pi. Right? So if one guy is here, the other guy is necessarily diagrammatically opposite. So there is a pi difference in quasi-energy, okay, to all of this, right? So you already get this picture, which I drew there. So of course, there are many such states. I mean, how many number of sigma z things can you get? Suppose there are n size, you will get 2 raised to the power n such configurations, right? So you'll have a huge number of points here. So I'm just drawing some. But whatever it is, there is always some plus cat state, and there is always some analogous minus cat state, and they always differ by a quasi-energy of pi in this solvable problem. I hope till now it's all okay. This is just very simple algebra. But it's very interesting that that super complicated structure that I was demanding just emerges from this simple trivial problem. But of course, it's a solvable problem. You might not believe that this structure would be stable, right? So what gives it stability? Anyway, so now let's discuss that. So now let's turn on a small, remember that term in blue that I wrote? This thing would of course make it interacting, right? Because now things are not diagonal in the sigma z basis. If I turn this thing on, this would make it interacting. So now let me turn on a small h. So when I say small h, what I mean is that this h, which is the width of the distribution from which I'm drawing these random numbers, this width of the distribution is very small compared to the typical values of this coupling as well as the typical values of that coupling, okay? So in principle, I can think of doing a perturbation. So you do that, and also if you want, you can try to make this pi pulse also change, right? So you can change this pi pulse to something like this, something like this. Okay. Now, the point is, this problem has MBL, right? Because this is perfectly localized in this thing, and I'm turning on a small perturbation. So this localized non-interacting problem goes to a many-body localized problem, right? But in MBL, we know a very important thing, that local in space perturbations perturb things only locally in MBL, right? So whatever these macroscopic cat states are, they can only be perturbed locally, right? So they'll change a bit because this is an interacting problem. But whatever these macroscopic cat states are, they'll only be locally perturbed. But remember, I already told you that macroscopic cat states have some properties which are highly non-local. What are those properties? One property is that 2-point correlation functions, connected correlation functions, do not decay as a function of distance to 0. Second property, which is even more weird, is if you calculate the mutual entanglement between a region A and B, and if you just separate them to infinity, the mutual entanglement does not go to 0. Whereas so you see, so even if you do some local changes to your wave functions, these two properties cannot be erased. It's impossible, right? So that actually means that even in this extremely complicated problem, this structure has to remain. So what am I using? Let me say it again. When I turn on the small HIX, this Anderson localized problem becomes a many-body localized problem. But in a many-body localized problem, we know that if we turn on a local perturbation, this is after all a local perturbation, because remember I told you a sum of local terms is also a local term. So this local perturbation can only do fluctuations locally. So what does that mean? That means that these macroscopic cat states would remain macroscopic cat states. They cannot suddenly become short-range entangled states. Because, because of all these properties and so this property that, so to change a macroscopic cat state into a short-range entangled state, you have to do something much more violent, okay? So this perturbation cannot do it because I'm assuming that this is many-body localized.
Some non-local perturbation.
Or rather, you have to cross some phase transition, right? So actually, I did not discuss that, but this log2 also comes because of some topological reason. I don't want to discuss it here. So this log2 cannot suddenly change to 0 by any perturbation. So make this log2 change to 0, you have to cross some kind of a phase transition, okay? So anyway, so this picture will change in some non-trivial way. Earlier, I could calculate all these energies. Now, these energies would be very hard to calculate. I have to use a computer and only then I can calculate these energies. And these eigenvectors would also become more complicated. So these energies would shift in some complicated ways. Maybe this guy shifts like that. And these are some complicated ways in which these will shift as a function of this HIX. But whatever happens, this picture will remain. This wheel picture will remain. Corresponding, so these will all be cat states corresponding to 1 plus type cat state. There will be its Z2 partner, okay? And similarly, if you move this thing by this amount, this thing moves by that amount. So there will be this pi difference. So once this thing is there and there is this pi difference, it's very easy to see just from that argument that I gave, omega plus and omega minus. It's very easy to see that if the difference of omega plus and omega minus is pi, then the thing would not synchronize with capital T, it will synchronize with capital 2T. That's it, end of story. So this structure is stable because perturbations in an MBL phase cannot destroy the long-ranged correlations of the eigenstates, okay? So only thing they can do is what I have drawn here. They cannot do anything else, okay? And because this structure is stable, and because you get these macroscopic cat states, and because the energy difference is omega plus minus omega minus equal to pi, therefore if you start with any simple initial state, the simple initial state will oscillate between these macroscopic cat states, the local quantities, and it'll just give you these very interesting time crystals. So this was the argument. This argument certainly sounds very, very convincing, but of course, Else et al. Were very careful, and they also did a numerical study to justify that this picture does work. I'll now actually tell you what they did, and they did two things. One, actually both dynamical quantities, but both of them are very interesting, and let me just tell you about them. So, but just from this picture, you can guess another thing very easily. Just from the structure of the soluble point and the fact that the perturbations keep everything stable, can you guess the operator? Remember in my definition 1, I said that only certain specific operators may not synchronize. It's not necessary that all operators fail to synchronize. Can you guess what operators you should choose so that you see lack of synchronization in this time crystal? There's very obvious operators here. Sigma x, okay. But sigma x is not a very good quantity to choose. Why do you say sigma x? You look at expectation value of sigma x. That's what you mean. Okay. But look at your solvable point. Where is your solvable point? What are you looking at in the solvable point? Sigma? So yeah, so you're just slightly deforming the solvable point. So you should look at expectation value of sigma z rather, right? So in fact, the operator which would show you that this state does not synchronize is sigma z. So let me just show you how let me just explain how they did it. I mean, there's nothing much to explain. After all, there's a complicated numerical calculation they did. But I hope you understand the stability argument. This is really at the heart of it. So the only thing I used here is that in an MBL, a local perturbation only perturbs locally. From that statement, it is impossible that macroscopic cat states generated at the soluble point would get destroyed. That's it. So there is this inherent stability, and that's enough to give you MBL, at least in the small perturbation limit.
So any n with 2 to the power alpha structure.
Any what?
Any n. N equals to 2, you said trivial time.
Trivial. I did not say they are trivial time crystals. I said they are the simplest time crystals. Okay, yeah. It's not trivial. No, it could be 3 also. I said, no. I said n0 is an integer which is greater than 1. Yeah. There are, in fact, now other time crystals which have some even more peculiar structures. Let's not go there. But these are called discrete time crystals, these things. And the simplest discrete time crystal is with n0 equal to 2. You had a question?
You turn on HIX for each I or
For each I, yeah. Yeah.
I don't understand why it is local.
Oh, no. It is local because it's a sum of local terms. Yeah. Sum of local terms is also local. Yeah. It is still local. Yeah. It's sum of local terms is also local. Yeah. So this kind of a perturbation cannot destroy this macroscopic cat structure. Perturbatively, it cannot destroy it. Another way to think about it is that mutual information where A and B go to infinity and it's log 2, that log 2 cannot perturbatively change to 0. So, yeah. Okay. So, in the first reference that I gave you, the Else et al. Paper, they did the following numerical thing also. They took a system of L equal to 200 and they did some time evolving block decimation. Basically, it's some variant of DMRG. They did that and they could only go up till a certain amount of time, but that time was enough to show them what was happening. And then in their numerics, they took h equal to 0.3. So you see, this was the h, and I made a perturbative argument in h. In their numerics, they took h equal to 0.3. So that's a reasonably high number, right? And what else? They started with these kinds of states, cos of pi by 8 for some reason. I don't know exactly why, but anyway. Sine pi by 8. And you just, this is like a state in the block sphere, and you just repeat the state on all the L sides, okay? That's what they did. And then they sort of probed the dynamics. And they also did some disorder averaging, yeah. Because of course there's disorder here, right? So they did a disorder averaging over something like roughly 150 disorder realizations. So basically, they took one disorder realization, computed whatever local quantities they had to compute. So that's one graph. They took another disorder realization, again computed this, and so on. So they got lots of graphs. They averaged over all these trajectories, and that's the final thing that they displayed in their paper. Okay? I'm not taking, they took it. What? I said that. I said that they use some variant of DMRG, which is called, what is it called? Time evolving block decimation. Yeah, so they use this method. Yeah, they did not do exact diagonalization. In fact, I'll show a second plot in which they did exact diagonalization, and that's also a super interesting thing. I'll show why it's super interesting. See, okay, let me just write it. Time evolving block decimation. The limitation of this method is you can go to a reasonably big system size, but you cannot go for a very long time because there is some entanglement bottleneck. Okay, I mean, you have to keep on increasing the rank of something in their simulation, and you have to monitor it very carefully, and beyond a certain time, the rank just blows up, and then you cannot compute things so reliably. Okay, so anyway, so once they did all this careful thing, that's how the graph looked. And please note, h is not 0 here. H equal to 0 is the solvable point. H is 0.3, right? So of course they have to do numerics. I mean, that argument that I gave was pure thought, which is what they gave, but now they're substantiating it. So they have one plot in their paper, which basically looks like that. I'll show you. Whatever, they go till 30 in the units of capital T. So they go till 30 cycles, okay, roughly speaking. And let's say 1.0 and minus 1.0 are the extremes of the y-axis. So in the soluble limit, if you started with simple states, you would oscillate between 1 and minus 1, if you look at sigma z, right? But of course, here there should be quantum fluctuations which would reduce the value to something. In fact, for these parameters, it reduces the values to something like 0.6 and minus 0.6. Okay? So, if you look at sigma z, then they got something like this. The interesting thing is, it does not synchronize at t. I mean, of course, I'm drawing a schematic, but this is close to what their numerical plot is. Okay, so important thing is it does not synchronize at t, it only synchronizes at 2t. So if you look at the points separated by t, they flip in sign. But if you only look at points separated by 2t, then they have the same sign. For example, this guy, so for example, this guy, this guy, this guy. These are separated by 2t. But this guy, this guy, this guy, these are also separated by 2t. But see, if you look at points separated by t, they are flipping in sign. So they are not synchronizing. So it's a time crystal. So this operator is a local operator, and it distinguishes this lack of synchronization. However, on the other hand, if you, for example, look at expectation of sigma y or expectation of sigma x, you notice the following. So I'm just searching for some chalk. So for example, you notice the following. We'll just go to the trivial value of 0. So it doesn't show this lack of synchronization. So maybe this is sigma y, and there's something similar for sigma x expectation. Okay, so, but that is also something I could have guessed from the soluble limit. The natural operator to show lack of synchronization is expectation sigma z, right, which is this. Okay, good. So that's that. Of course, if you are a devil's advocate, you could have said, oh, but how do you know that maybe if they push their time scale to something even longer, that this phase would melt away? How do you know that this does not happen? Of course, I don't know, and neither do they. But they did another interesting thing, which is actually very, very interesting. So they did some exact diagonalization study as well. Like when they wrote the paper, they just did 8, 10, and 12 chain lengths. Okay. But the advantage of exact diagonalization is they could go to arbitrarily long times. And then they saw something very interesting. So let me again tell you the observable they looked at and plot the thing and tell you why what they saw was very interesting. Because I would make an exact analogy to this tunneling term that I introduced a tunneling time in the Z2 symmetry breaking, right? And that increased exponentially in L for a Z2 symmetry breaking, right? Here also there is, morally speaking, some Z2 symmetry breaking, but a more abstract one, right? Because there are all these doublets which are forming, right? You will see a sort of a tunneling time emerge even here. Yeah? What is very specific? What is very specific? Oh, no, no, no. That is not, no. They just made this particular choice in their paper. As I said to you, I don't know why they made this choice, but no, this is not. Because they did a lot of different disorder realizations. So, the microscopic energy landscape is different and all that. So, then they averaged over all of these. And that is the final graph that they produced. So, it's not sensitive to those details. All the trajectories must be doing this. Otherwise, this feature will be washed out upon averaging. Okay. Yeah? N not to be 2. Oh, I see. So then, okay. I mean, see, here N naught was naturally true because in the soluble problem, N naught was 2. So the trick is you think of another soluble problem where N naught is 3. Maybe you think of some Potts kind of a theory or whatever, and then you perturb it. People have actually played that game and have got N naught equal to 3 time crystals as well. Yeah. But that's not the main point. The main point is once you realize this logic and these guys realize this, right? So. Of course, the unit circle is a property of the Fluke structure. Because for any Fluke unitary, the eigenvalues live on a unit circle. Yeah. So for N naught equal to 3, see, for N naught equal to 2, you get a rod, and the rod has a rigidity. The rod has a rigidity. See, any symmetry breaking, there's a notion of rigidity. For N naught equal to 3, you will get a rigidity of some structure like this. But still, the 3 dots would still be macroscopic cat states. That's the important bit. Okay, anyway, let's just discuss this. This is already very interesting. Okay, then they looked at exact diagonalization. And in the exact diagonalization, they defined an interesting quantity, which is the following. Z of t. So some time-dependent quantity. I'll explain what this is. And of course, they chose to look at the sigma zt object because they realized by now that that's what shows lack of synchronization. So let me explain this thing. So firstly, this t that they took, this time that they took, they really took only stroboscopic times. So that's the first thing. T is not like a running index. T is only 0, capital T, capital 2T, 3T, and so on. Even though that may not be completely obvious from the graphs in the paper, but they just took these things. Okay, that's the first thing. The second thing is, when they calculated it, there is this bracket. So what is this bracket? So they take a random initial state and they calculate this object in that random initial state. And why did they introduce this sign here and this thing here? Because see, they want the signal not to be washed out. See, the thing is switching in sign as a function of stroboscopic time. That's why they have this phase factor here, and that's why they have this sign here, so that everything is positive definite. See, I could have started with some other initial state, which is like a Z2 partner of this, and then everything here would have reversed. Everything here would have reversed. I would have gotten something like, so maybe some other color. Something like that. You see what I'm trying to do? If I took some other class of initial states, which are sort of mirror images of those initial states, okay? But to alleviate that, they just sort of put the sine function here, and they incorporated this thing here to take care of the switching. Okay. Then for each disorder realization, they averaged over several random initial product states, and then the disorder averaged over 500 disorder realizations. Okay. And after doing all that, they got this quantity in their exact diagonalization. Okay. Now let me show you how this quantity looks. So I would need 3 colors now. Okay, 1 color, 2 colors, white. Okay, anyway, let's see, white is fine. So, okay, this is fine. So now let's see how this quantity looks like. Of course, this Z of t starts from 1 or whatever, yeah. And then this is on a log scale. This x-axis is on a log scale. So 10 to the 0, 10 to the 1, and they go all the way till 10 to the 12. So 10 to the 12 stroboscopic drives. But they can do that because they're doing exact diagonalization, right? So now let's see what happens here. So this thing hits a non-zero plateau, and then it decays. The sign of decaying is almost like saying that the time crystal is melting, right? Because if the structure is lost, then ultimately this thing will be washed down and will average to 0. So this, yeah. Then if you go, so this is, let's say, L equal to 8. Then let's say you go to L equal to 10. So for L equal to 10, you see a bigger plateau in time, and then again it decays, something like that. But a bigger plateau in time. And notice this is a log scale. And then, so this is like L equal to 10. Then you go to an even bigger size, which the biggest they could do at that time. And you see something like that. And this plateau time, you could roughly fit to exponential of L. So you see that the melting time of the time crystal in a finite lattice seems to scale as exponential of L, which is again related to the tunneling time of conventional phase transitions. There's a direct corollary there, right? So those 2 plots were the plots which convinced many people that, of course, this is correct and this is correct. At least if MBL is correct for whatever system sizes they are using, the rest of the arguments is correct. Okay? Good. So I hope you see why this is a time crystal. Okay, so in the remaining short time I have, let me explain another thing to you, which is anyway a very important topic which I didn't have any time to cover, which is pre-thermalization in Fluke systems. And I'll just very quickly tell you how to stabilize a pre-thermal time crystal without any disorder. Okay? Maybe I'll go 5 minutes or something over time, but let me just do that, just to give you a flavor of how things work. Okay? But if there are any questions till this point, please ask me now. So this is how one thinks of the simplest time crystals. So these are Fluke MBLs with an extra structure. What is the extra structure? That the eigenstates of the Fluke unitary are macroscopic cat states. That's the extra structure.
So I understand that they fitted an exponential of these 3 points, but like, is it impossible that after at larger range, this time saturates?
No, it's not. But you see, nobody can answer that. See, the only way to answer these questions is to solve a theory analytically. If you cannot solve a theory analytically, you cannot answer these kinds of questions. Okay. Right. So in physics, you just do the best you can. Yeah. Okay. Any other question? Okay. If there are no questions, then I assume it's clear. Okay, let me keep that for dramatic effect. Okay. So let me quickly explain this pre-thermal thing. Maybe I don't have any time to show the steps to you, but let me roughly explain the logic to you, like from a bird's eye point of view, and then I'll stop. So by the way, one thing, if this MBL is stable at arbitrary length scales, then this lack of synchronization will go on for arbitrary times, okay, for a very big system also. But of course, I mentioned the caveat, right? It crucially relates to the stability of MBL. Okay, now let's talk about some pre-thermalization. So of course, here I could conceive of this phase, because as I said even in my first lecture, if at the start some theory has some non-ETH-like features, then it may happen that when you put a fluke structure on it, the non-ETH features survive, and therefore fluke ETH is violated. Okay? But then you can ask the question, okay, if I have a theory where there is ETH, then can you nonetheless get some non-trivial phases in a fluke-driven matter? Answer is yes. And actually, it's a really big open area. So maybe I'll just write it here. Lots of open questions. Of course, I did not have too much time to get into it. So one thing which people definitely realize is the following. If you have a problem in which this thing, the drive frequency, just 2 pi by t, is much, much larger than all the energy scales of your local Hamiltonian, in this setting, people understand pre-thermalization quite well. This is a setting where they understand it very well. This is known as pre-thermalization at high drive frequency. So in this setting, as I said, your drive frequency is the dominant scale. It's much larger than all the energy scales of your local Hamiltonian. Okay? So in this setting, what happens is the following. Suppose you look at some local observable stroboscopically in time. Then what typically happens is the following. So maybe I take a local observable where, just for simplicity, that local observable, when you have fluke ATH, has expectation value 0. Let's just assume that without any loss of generality. Then in this regime, something like this happens. It goes to 0, but in this peculiar fashion. So first, there is a quick transient, and this transient is an order 1 time. So order 1 meaning order 1 in these time scales, inverse of this or whatever, right? First, there is an order 1 time transient. So this is some quick transient, and then this expectation of O seems to stick to some particular value. So it seems to go to some stationary state. But after an even longer time, T star, which scales as exponential of omega d, then the system realizes, oh my God, I need to fluke ETH. Okay, so it fluke ETHs. Okay, so anyway, so that's the point. So it just flows to a completely featureless steady state. So there is a big time window where something else happens. Okay, of course, this time window is not dependent on system size, so it does not diverge to infinity in the thermodynamic limit, but it can be a reasonably large number. So in this time window, you can actually define the dynamics through a effective Hamiltonian. Okay, and really you can write u of t as e to the minus I in this regime, where is local in real space. Now this is very important, because as I told you in my first lecture, if you try to write a Fluke Hamiltonian, and if you really think hard about Fluke ETH and the absence of any conservation of energy in this Fluke setting, actually this Fluke Hamiltonian may be some horribly complicated non-local object in real space, okay? But the fact is, in this regime, you can find some like local in real space Hamiltonian, and then this is something which you can sort of understand through ETH-like considerations. You understand why I say that, right? Because ETH deals with problems exactly like that. Okay? Good. So let's try to understand it a bit more. So you see, I'm talking of high drive frequency, which means that this T is a small number. So to compute this H effective, it sounds very reasonable that you need to set up a perturbation theory in terms of the small parameter being capital T. Okay? So if you do that, then the perturbation theory can be set up like this. And this is nothing but what is known as a Fluke-Magnus expansion. This is something known as a Fluke-Magnus expansion. I'm really sorry, I unfortunately don't have any time to tell you about technically how to do these things and many other approximation schemes for the Fluke Hamiltonian, but I'll just do some self-advertisement now. So if you want to learn those tricks, there is a review by me, Deeptiman, and Krishnendu, and I've forgotten when I wrote it. But anyway, if you search review and search for these three names, there's only a unique hit that you will get. So, okay. So anyway, there are lots of algebraic schemes to do various perturbation theories, right? So you can read about many of them in this review. But I don't want to inflict that upon you at this late hour. But the important thing is that such a perturbation theory exists. In fact, the simplest variant of this is that if you take a Fluke unitary which has these piecewise parts, so that you can write the Fluke unitary as some product of U1 and U2, where the coupling is constant over one half cycle and another constant over another half cycle. In fact, this formula reduces to something known as the BCH formula, which you are all well aware of, right? Good. And you know that in BCH formula, as Shubhrata also mentioned, as you go to higher and higher order terms, things become more and more non-local, right? And that's exactly why ultimately the Fluke Hamiltonian should also be a highly non-local object. So what saves you here? Well, you're not saved here. It's just that there is a regime here. But this is a property of many perturbation theories in general many-body physics. So what saves you here is the following. So you see there's a giant series here. So how do you do series analysis for any series? You just take the nth term and you just plot the norm of it, right? You just plot the norm of it. Let's say I draw a graph of this as a function of n. Now the point is, in this limit which I talked about, where omega d is much higher than all scales of the problem, initially you see a wonderful thing. Terms are getting less important as the order of the series is increasing. That's remarkable. So you think, oh my God, I'm lucky, this is a convergent series. Good. So you can be happy till your happiness lasts. So actually you do this, and then ultimately you realize, no, this is a divergent series. But this plateau, in this plateau, you can still describe the effective Hamiltonian by truncating this series. This happens in many other contexts in physics, okay? So this is really what happens. So in this plateau, you can truncate this series to some n naught. And when you can truncate the series, then you obviously have a local Hamiltonian by definition, right? By definition. Good. And actually, all this was shown in a really tour de force paper. It's really a tour de force paper. You should read this paper if you're interested in any of this. So, okay, good. But now it seems like I have reached a dead end. Why? Because you see, okay, well, it's not really a dead end. I can still get interesting physics from various kinds of H effective. But unlike the anomalous Anderson insulator, or unlike the time crystal, where there was some structure which was inherent to the fluke nature of the problem, here I seem to have reached a dead end. Here I'm saying, oh, there is a local Hamiltonian, and the dynamics here looks like it's being driven by that local Hamiltonian. So it seems like I'm back to an undriven problem, and I, in this pre-thermal window, should get no physics which cannot be described by some equivalent undriven problem. But fortunately, the situation is not so bleak. So one example where you can get around this dead end is you might have a high frequency expansion again, but not in the lab frame, but in some other effective frame. And then when you convert the theory in the lab frame, you might have something very non-trivial. Okay, so that's one way of getting out of this. So in fact, that's the way of stabilizing a time crystal, but I see I'm completely running out of time. So let me just give you the basic, I don't even know, bare bone of the thing and then just stop, okay? But really the point is to stabilize things beyond this undriven paradigm here, what you need to think about is you need to think about situations where the high frequency expansion is not incorporated in the lab frame, but there is some other effective frame in which somehow you do a high frequency expansion. And then when you switch to the lab frame, then something more non-trivial emerges. And typically in all those problems, what happens is, unlike this problem where all energy scales were much smaller than the driving frequency, in those problems, which I just now am alluding to, there are some energy scales, maybe 1, maybe 2, or whatever, maybe more, some finite number, which are of the same order as omega d. So then you cannot do the standard high frequency expansion. You have to do something non-standard. So, but let me just give you this one example of pre-thermalization where you don't need even disorder and you get a time crystal, and then I'll stop. Oh, by the way, I should have mentioned. So, of course, whatever initial state you start with, you can calculate its you can calculate for that initial state this expectation value, knowing this operator, knowing this local operator, and that determines the effective temperature here. And that fixes all the average expectation values of all operators, all local operators in this regime. Okay, that's actually a non-trivial statement because you see, you're actually truncating the series expansion. So the many-body unitary is completely different to the unitary you obtained after truncation. But somehow magically for local operators, this truncation does not matter. And that is another non-trivial thing that was shown in that paper. It's not completely obvious. Okay, so. So Shamik, maybe I'll take 10 minutes more. Or who's the chair? I forgot. Can I take 10 minutes more? I'll give you a candy afterwards. No, it does. As I said, you calculate, so somehow you have to calculate this operator that you can calculate by various methods. You can see this paper or see my self-advertised review, okay? But whatever, you just calculate it, some calculation, okay? Then once you calculate it, you calculate this expectation value. If you happen to take some initial state different from me, which has that same expectation value, then the average values of the operators would be the same in the pre-thermal phase. But if you happen to take an initial state which has a different energy density with respect to that H effective, then you'll go to some different pre-thermal thing. But that pre-thermal thing will be controlled by this operator only, H effective. Okay? So now I'll go to a problem where you cannot straightforwardly do you cannot straightforwardly do this high frequency analysis. But if you change your frame, then you can. But of course, I won't be able to give you the details. I would just really mention the bare minimum. Okay, so these are called pre-thermal time crystals. And again, there was another set of paper by the same set of authors, which is a very beautiful paper. I forgot there's some PRL, I think, but anyway, I have the archive number on my notes, so it's okay. So what happens here is the following. So again, let's say we think of trying to stabilize a pre-thermal version of these discrete time crystals where expectation value of sigma z is the correct operator to look at. Then, the first thing is, the mechanism they talked about is not valid in 1D, it's valid in 2D and higher. See, this is already interesting because in this school, predominantly we have been talking about 1D systems only, right? But this is a mechanism which is valid in 2D or higher for short-range interacting theories. Or if you want to take 1D, then you have to take a long-range quantum Hamiltonian. Then this mechanism is valid. Okay? So again, you take your initial state and you look at expectation value of sigma z, and then what you see is the following. Let's say this is 0. There's a quick thermalization, and then something like this happens. There's a big plateau. Something like this happens. So for even stroboscopic times, maybe you stay here. And for odd stroboscopic times, you just stay on the reverse values. Okay? And then this thing is also some exponential of omega d, this time window. And after that, you melt away. You go to fluke AETH. But this thing is actually dependent on the energy density of the initial state. That's the interesting bit. This phenomenon only happens if the energy density of the initial state is reasonably low. Energy density can always be associated to a temperature. So basically, I'm saying that this phenomenon happens only when in the equivalent 2D or 3D problem, there's actually a thermal phase transition. And the phase below the thermal phase transition breaks discrete Z2 symmetry, and above the thermal phase transition does not break it. That's why I said this phenomenon cannot happen in 1D, because in 1D there is no thermal phase transition in a Z2 theory, right? Okay. So if you take, but we know, for example, in 2D what is Tc for some model, in 3D we know what is Tc. These are all some order 1 numbers. So if the energy density of the initial state is less than that order 1 number, this will happen. If it's more than that order 1 number, then the following will happen. In the same setup, with the same Hamiltonian. So basically you would see no difference of T and 2T, and it'll just be some normal pre-thermal thing. Whereas here it's a pre-thermal time crystal. So since I know that I have no time to tell you any details here, roughly speaking, in this problem, there is one coupling in the Hamiltonian which scales as omega d, and the rest of the couplings are much smaller than omega d. When you solve for the effective Hamiltonian in the pre-thermal regime, but you have to change your frame to do that because of this, then when you go back to the lab frame, something very interesting happens. So when you go back to the lab frame, then the Fluke Hamiltonian in this pre-thermal regime starts looking like this. So you see, normal pre-thermalization, you would have just gotten a Hamiltonian like this. But then here there is a non-trivial operator x multiplying it. What is that x here? It's something which I have explained before. It's that pi pulse. What does this operator x do? It does something very dramatic and non-local. If you give it any sigma z configuration, it just flips it, right? And then flips it back and so on, okay? And something else also happens, which is very non-trivial, which is again an emergent property. This x commutes with this d effective. So basically, if you can interpret this x as some symmetry, and the symmetry can be broken or unbroken, then you can get physics beyond just the physics here. Okay, so roughly speaking, if this symmetry stays unbroken, then this x can be thought to be identity, or the action of this x can be thought to be identity, because nothing is happening, no symmetry is being broken. But when the symmetry is broken, then this x has a very non-trivial operation on your states. Okay, so now I think I'm really late. I'll just draw a picture and stop. Okay, so yeah, but I hope you get at least some sense, and you get some sense of why this initial state's energy is important, right? Because if the initial state's energy is below, so again, when I take the initial state, I have to compute its energy with respect to this d effective. And that may be some 2-dimensional or some 3-dimensional theory, but that gives me an associated temperature. If that temperature happens to be above Tc, then the action of x is trivial. Then it's this regular stuff. But if the energy density happens to be with some temperature associated below Tc, then you see all these interesting things. Okay. So lastly, I'll just draw a picture and stop. So if you take a state like this, whose initial energy density happens to be associated with a temperature scale which is lower than the critical temperature associated with this d effective, and d effective is after all a local Hamiltonian, then something like this happens. There's some initial state. There's a quick transient, that transient, and then it enters a limit cycle. Where this x keeps toggling the states effectively like this. They keep toggling the states effectively like this, and therefore they fail to synchronize. And after this pre-thermalization timescale, the system again realizes, oh my God, I need to flow to infinite temperature, which is this. Okay? And so, in this mechanism, you don't even need disorder. All you need is that there must be some other clever frame, not the lab frame, where you need to set up your high frequency expansion. And then when you go back to the lab frame, then such a structure emerges where, if you're lucky, this X can be interpreted as a symmetry. And then when you start with states where the symmetry is broken versus where the symmetry is unbroken, there's a big difference. And these three gentlemen formulated a problem, also did a lot of beautiful analysis and also numerical studies where they showed these things very clearly in the paper. So I'm sorry for being over time, and maybe this is a good point to stop my lectures. Yeah.